So you're ready, Nabil? Or?
Yeah.
Okay, so welcome everyone. We are very happy today to have Nabil Iqbal, who will tell us about mean string field theory. So as usual, just everybody unmute yourselves whenever you want to ask a question, and otherwise, Nabil, the floor is yours. Go.
Thank you, Daniel. Thank you very much for the introduction and for inviting me to be here. So the title of my talk is Mean String Field Theory. Before I begin, I'm going to say something that I always say during all these Zoom talks, which is I still find them weird, even though we've been doing this for a while. It's a lot more fun for me if it's more interactive. I feel less like I'm just talking into a screen. So please, I would like the barrier to asking questions to be very low. Please feel free to chime in with questions, comments, anecdotes. It's all fine. Please just jump in. Okay. So with that out of the way, let's get started. The title of my talk is Mean String Field Theory. This is some work that I did in collaboration with John McGreevy, and we are hoping the paper comes out very soon, but let's see. Okay, so let's get started. So this talk is really in 3 parts. I'm going to begin with a sort of very lengthy motivation. In this motivation, I'm just going to talk about symmetries in general and why we like them. And I think most of what I'm going to say in the motivation at a technical level, people are already aware of, but I'll try to say it in a way that lets me generalize it to what's going to come next. I will then talk a little bit about higher form global symmetries. Now, I know many people in this audience might already know what these are, but just in case, I'll remind everyone what a higher form global symmetry is and what it means and what it's good for. And then the final part, I'm going to talk about mean string field theory, which is really the new contribution of our work. So I'm going to explain what mean string field theory is and why it might be useful for many different things. But let's get started with an overview of global symmetries. So first of all, symmetries are important. I think everyone agrees on that. So let's begin by just reviewing a few very basic things about ordinary U1 symmetries. Okay. So think about your favorite quantum field theory that has a U1 global symmetry. If it has a normal U1 global symmetry, it'll have a conserved current J. Let me just confirm that you can see my mouse. Is that right? You can see my cursor? Okay.
Yeah, we can.
Good. Okay. So you have a normal U1 global current J. The current has 1 index, and the current is conserved. Okay. Now, this is the conservation equation, grad mu J mu equals 0. If you're into differential forms, you can write this in form language as D star J, where J is a 1 form. Okay. Now, what does a current do? Well, an ordinary current counts particles, right? Like, for example, if you have a box full of particles and you want to count them, what you do is you integrate over all 3 dimensions of the box, and every time you get a particle, you count 1, 2, 3, 4, 5, 6, 7, 8. And that particle number is conserved, which means that if you do this once and you do this at a later time, you get the same answer for the number of particles. Okay, this is a very basic fact about conserved charges. And there's a fancier way to say this. A fancier way to say this is that you integrate star J, the differential form, over a 3-dimensional manifold, for example, a constant time slice, a codimension 1 slice of space-time. And then because D star J equals to 0, if you do that integral once, you do it at a later time, you'll get the same answer because this integral is invariant under small deformations of the surface. Okay, this is a fancier way to talk about global symmetries, about conserved charges. In this picture, there are some particle world lines, and we're sort of counting their, this is the integral, and every time we get one, we count 1. If you move this guy up in time, because the world lines don't end, you get the same answer. Okay. Now, another very basic statement about symmetries. What is charged under a U1 symmetry? We count particles. The thing that is charged is the object that creates particles. So local operators create particles, right? If you want to make a particle here, you act as a local operator at this point. It makes a particle and goes off and does its thing. And what that means is local operators are charged under global symmetries. There's a formula for this. This is the Ward identity for the conservation of the current in the presence of a charged operator. And the point is the current isn't exactly conserved if you have the charged operator. Instead, it's only conserved up to a delta function term, okay, sort of contact term. And finally, here's something that's going to be useful later. Local operators are 0-dimensional things. And for that reason, we're going to call these symmetries 0-form symmetries. Okay? And the whole point, of course, is that we're going to take that 0 and make it something higher in the next part of the talk. Okay, so that's basic facts about symmetries. Now, what are global symmetries good for? Landau told us that we can use global symmetries to classify the phases of matter. So let me remind everyone what this means. There are basically two things that can happen if you have a global symmetry. There are two basic phases. In one phase, your symmetry can be unbroken. That's kind of like the default case. If the symmetry is unbroken, you should imagine that the charge excitations are gapped. And what that means is charge correlation functions decay exponentially in space. So for example, the idea is if I want to compute O dagger O, if I activate the operator O here, that creates a particle. The particle sort of has to go over here to O dagger, but that costs some action because the particle is massive, and the whole thing ends up being suppressed exponentially in the mass of the world of the particle. Okay, this is what it means for a symmetry to be unbroken. The other thing that can happen is the symmetry can be spontaneously broken. In that case, the idea is that the particles that you're counting with the symmetry have condensed, right? And then what it means is operationally is charge correlation functions factorize. In other words, if you compute O dagger O now, you try to separate these insertion points by a large distance, what's happening is that O dagger O will eventually factorize into a product of two O daggers, an O dagger and an O, but each of these has a non-zero VEV, which means this thing doesn't vanish. Instead, this correlation function saturates at a large distance and becomes independent of the insertion points. Okay? This is, of course, very different from the previous case, where no matter how far apart you move them, if you double the distance, the correlation function becomes smaller. That's not the case here, it saturates. So these are the two basic phases that you can have. And finally, one more possibility is you could sit right at the transition point between these two things. In that case, your correlations are sort of halfway between these two. It's not constant, it's not exponential, it's like a power law. Okay? So these are the three rough possibilities, of which these two are the phases. Are there any questions at this point before I move on? Is everyone happy with this? Okay, very good. So now, if you care about the phase transition, there's a very useful thing you can do. What you can do at the phase transition point is you can often define a sort of universal Landau-Ginzburg type field theory to describe the transition. So how does this work? Well, the rule of the game is really the following. What you do is you introduce a sort of general order parameter field, okay, which I've called phi here. And the point is that phi transforms linearly under the symmetry. Okay, so for example, phi goes to phi times e to the I alpha. And obviously this field is a map. It's a map from the space of points to the complex numbers. It must be the complex number so it can transform linearly under my U1 symmetry. And then what you do is you just start to write down every possible term that is consistent with the symmetries. Okay, so for example, you have a kinetic term, you have a mass term. You cannot have a cubic interaction because a cubic interaction, phi dagger phi phi, would not be invariant under the symmetry. You can have a phi to the fourth interaction, and so on and so forth. And you write down all these things. And then the idea is that close to the phase transition, independent of your microscopics, your transition will be described by this universal Landau-Ginzburg type field theory. Okay. For example, if m squared is greater than 0, my potential has a unique minimum, and you sit at the bottom of this minimum, and the VEV of phi is 0. This is the unbroken phase. Okay. On the other hand, if m squared is negative, then my potential has this sort of Mexican hat minimum. And now you sit somewhere at the bottom of this potential, and now the VEV phi is going to be non-zero. This is the spontaneously broken phase. Now, you see, the sort of remarkable thing is that at the critical point, which is mostly m squared equals to 0, the properties of the phase transition, you know, the divergence of the correlation length, the thermodynamic singularities, the specific heat divergence, all that stuff, are all described by this universal field theory, which does not know about your microscopics. Okay, you can talk about like superfluid helium or the XY model, and you can still write a general continuum field theory to describe it. Okay. Okay. Now, this Landau-Ginzburg theory is useful for a bit more. It also provides a useful low energy description of the condensed phase. So imagine that m squared is negative, so my potential looks like this. Then, you know, my field phi wants to condense. It wants to roll down to the bottom of this. But now there's a low energy degree of freedom, which is the phase rotations of my field phi. Okay. What you can do is you can write this ansatz and plug it into this action. And then if you go through some tiny algebra, you find a action for the gapless Goldstone mode theta, where you can derive this action from this Landau-Ginzburg theory. Okay. And it turns out that this low energy physics is completely determined by this pattern of symmetry breaking. All right, this Goldstone mode physics is determined only by the symmetries. You don't need to worry too much about the microscopics again. Okay. So these ideas that I've just told you about, these basically form the Landau paradigm of physics. Okay. The Landau paradigm is basically the following two ideas. Phases of matter are classified by their patterns of broken and unbroken symmetries. Okay. In the U1 case I just told you about, where that U1 is a number current, we would call this a superfluid. A superfluid is where your number current is spontaneously broken. If you think about the phases of matter that you know and love, okay, this depends, of course, on what phases of matter you love, but most of them are classified by their symmetries in a very normal way. For example, a solid is a phase of matter that spontaneously breaks a translational symmetry. A liquid is a phase of matter that doesn't do that, okay? And so on and so forth. And furthermore, critical points between different phases can be studied by universal Landau-Ginzburg type theories of the order parameter, okay? Where you don't care about the microscopics. These two ideas are extremely powerful and they work spectacularly well for many, many, many phases of matter. And of course, this is the foundation of textbook condensed matter physics. If you open any textbook on condensed matter theory, this is like chapter 1. Okay, maybe before going on to however, I should ask, are there any questions about the Landau paradigm, the conventional Landau paradigm, before I move on? Everyone happy? Okay, good. So, however, much modern work in condensed matter theory involves phases and transitions between them that do not fit into the normal Landau paradigm. Okay, so one example of this is topological order. So it turns out if you Google topological order in Google Images, you get this pretzel. I think it's because the things in the pretzel are winding around each other. But anyway, whenever you see this pretzel in this talk, it means there's something topological happening. Okay. So what is topological order? For example, this is basically things having to do with lattice gauge theory or with gauge theories of some form. For example, the fractional quantum Hall states are a real life system that exhibits topological order. Lattice gauge theories also exhibit topological order. It's a phase of matter that does not have a local order parameter, but is still interesting. There's something fun going on. Okay. And there are many others as well. You know, there's lots of things that people in this audience will know about. I don't have much to say about them in this talk, so I won't go into that now, but there are many things that don't fit into the normal Landau paradigm. Okay. So what this should suggest is it should beg the question, can we do better? Is there a larger framework that we can build that will contain, that can enlarge the Landau paradigm to include things like this as well? Okay. So that's the overarching question that I want to address, and I'm going to do that with a very specific tool. Okay. I realized that I can't see the chat. But okay, there's not much there.
I will pay attention to the chat. Now,
okay.
The only message there is just a link to your slides.
Oh, perfect. Thank you.
Sorry about that.
Great, no worries. I just saw the one message. I thought I should look. Okay, great. So, so now moving on. So how do we do better? How do we enlarge the usual Landau paradigm? And the way to do that is through higher form global symmetries, which I will now tell you about. So the idea behind the higher form global symmetry is very simple. And this is something I first learned about from this very nice paper by Gaiotto, Capustin, Seiberg, and Willett in 2014. The idea is that you can have global symmetries that are different in that, for example, their currents will not have just one index, but two. Okay. This is the idea behind, well, the idea is a bit deeper than that. This is the manifestation of a so-called higher form global symmetry. So now I'm going to tell you a little bit about higher form global symmetries, just to set the stage. So a higher form global symmetry has an anti-symmetric higher index current, like for example, this J mu nu. In fact, in the rest of this talk, we're going to study precisely such two index currents. So imagine a two index current. This is a differential form that is conserved. So grad mu J mu nu equals to 0. Now, what's interesting is if you like differential forms, of course, you can write this equation exactly the same way, d star j equals to 0, except that j now is a 2 form and not a 1 form. But the conservation equation looks exactly the same. Now, what does a two index current count? A two index current counts strings, okay? They don't end in space or in time, okay? So there's strings that have no end. You should imagine that the extra index here, mu, tells you which way the string is pointing, okay? That's what this thing tells you. And let's think for a bit about what a conserved string number means. Remember before I was counting particles, so I was integrating over a volume. But imagine you have a bunch of strings coming out of your laptop screen pointing towards you, and say you want to count those strings. How do you count them? Well, you don't need to integrate over the full room because the strings don't end, right? So you can just integrate over your screen, and every time a string is poking through the screen, you count 1, 2, 3, 4, 5, 6. And then you can move that screen towards you in space, or you can move it upwards in time, and you'll always get the same answer. In math, what that means is you don't integrate over a codimension 1 manifold, you integrate over a codimension 2 manifold, but you integrate star j. And now as you deform this manifold in space or in time, you always get the same answer for this conserved string number. Okay. So now what is charged under a higher form symmetry? The thing that is charged is the object that creates the thing that you count. Okay. Now you're counting string worldsheets. How do you create a string worldsheet? Well, if you want to create a string, what you have to do is you have to act with a line operator, right? You act as a line operator on some one-dimensional line, then that creates a two-dimensional string worldsheet that moves off and does its thing. And what that suggests is that line operators should be charged under a higher form symmetry. So here's the equation for that. In the presence of a line operator, which I'm calling WC, where C is a one-dimensional curve, grad mu j mu nu is not 0. It's only 0 up to a delta function with support on that curve. And I have an extra index here I have to deal with. That extra index comes from the geometry of the curve. Okay, that's why there must be a one-dimensional curve there. And you can make this equation actually correct. This equation right now is schematic. Because lines are one-dimensional, such symmetries are called one-form symmetries. Okay. So this is if you have a U1 one-form symmetry, you have this conserved current. You can also have a ZK one-form symmetry. What that means is you don't have a conserved string number, you then have a conserved string number modulo K. Okay. This fact that it is line operators that are charged is quite important. So I'll pause again for any questions about this. Okay. Good. Let's keep going. What are higher form global symmetries good for? I want to stress that these symmetries are actually just global symmetries like any others, okay? They're not gauge symmetries in particular, importantly. They're really global symmetries. And the truth is, they do everything that normal global symmetries do. We should really rebuild all of that technology for these higher form global symmetries. For example, they can have anomalies. You can use those anomalies to classify phases of matter. They can have hydrodynamics. Some of you were here last week for a talk by Iqbal on exactly the hydrodynamics of a higher form global symmetry. What I'm going to do is I'm going to use Landau to try to use them to classify the phases of matter. That is what Landau wants us to do with any global symmetry. So we should ask, what are the two possible phases of a higher form global symmetry and what do they mean? So again, one phase you can have is when the higher form global symmetry is unbroken. In this phase, all the charged excitations, in other words, the strings, the things that you're counting, are gapped. What does it mean for a string to be gapped? It means that it has tension, okay? And in that case, your charged line operator, which W of C, is going to obey an area law, okay? So if you insert this into your correlation function, into your partition function, then the VEV of this line operator is going to decay like the area of the minimal surface that fills in this curve. And the idea is, of course, that you're making a string worldsheet with this line operator. That string worldsheet has a tension, and so you measure that tension with this line operator. If you think about it, this is the line-like analog of an exponentially decaying correlation function of local operators, right? Because it depends on what's happening in the middle. It depends on the geometric quantity that fills in this thing. Okay, so this area law is one of the phases. Phase is the spontaneously broken phase. And in this phase, strings have condensed, okay? They have no tension, that tension has gone to 0. Now, the idea of a condensed string might seem kind of weird and strange. What does that mean? So, more precisely what this just means is that the charged line operator does not have an area law, but a perimeter law at large distances, okay? And so that tension has gone to 0. Now this line operator, it depends only locally on the data characterizing the curve. The perimeter is only a local function of the curve, and so you can figure it out locally. And this is basically like having a factorized correlation function for local operators. It's the line operator analog of that. So I'm calling this the spontaneously broken phase. In fact, you can show, Diego Hoffman and I, and also Ethan Lake, have proven that there is a higher form Goldstone theorem, which means that if you have such a behavior for this line operator, there is a gapless mode in the spectrum. And I'll come back to this in a few slides from a slightly different point of view, but you can show that it really does deserve the name.
Nabil?
Hi, Blaise.
Hey, can I interrupt for a sec? I'm not sure I fully understand what you mean when you say it depends only locally on the line operator.
Yeah. What I mean is the perimeter you can construct as a local integral over data characterizing the curve. It's like integral, x dot squared, root x dot squared, right? It depends only locally on what's happening here. If you deform this a little bit, you can get the answer through a local modification of this perimeter functional. Okay.
And it wasn't the case with the area?
No, this is a very non-local problem, right? If I give you a curve to figure out the minimal surface that fills it in, it's quite complicated, right? You have to solve some Nambu-Goto action, there can be phase transitions and stuff like that. So these are different. I think this is the sharpest way to see this. This perimeter, it really depends locally on this. If I give you, x of c, you can just do one integral, integrate root x dot squared and figure it out locally by integrating over this. But it's not at all true of the area. This is hard. Does that make sense? Okay, good. Any other questions? Yeah, maybe it's a good place to say I wrote perimeter. The truth is, any local functional of the curve is okay here. You would generically expect the, like for example, you could also look at integral of the acceleration, the x double dot along the curve and so on. That's also possible. Okay, but the perimeter is the leading term in expansion. Okay, good. Any other questions? Okay. So now, this was all very abstract. Now, just to tell everyone that this might sound weird if you've not heard it before, but the truth is it's a very simple concept. And in fact, many theories that you know and love already have these higher form symmetries, okay? So let me give you some examples. The first field theory that most of us learn about is Maxwell's E&M, okay? We normally study it with charged matter, but Maxwell's E&M with charged matter actually has a single U1 one-form symmetry associated with the conservation of magnetic flux, okay? So if you have F, the two-form current for that is epsilon contracted into F, all right? This current is conserved just by Bianchi's identity, all right? Physically, what's happening here is that in normal E&M, magnetic field lines don't end because normal E&M doesn't have magnetic monopoles. So magnetic field lines don't end, and those are strings, right? Magnetic field lines are strings. Because they don't end, they result in a conserved charge, which is this one here, all right? The charged line operator associated with the symmetry is what's called the 't Hooft line, all right? It's a kind of disorder operator you can construct, it's a straightforward construction. And in fact, the photon, the normal photon that we know and love, can be thought of as the Goldstone mode, because in the normal phase of E&M, this symmetry is spontaneously broken, all right? So this is, I claim, the correct way to think about the symmetries that are present in ordinary Maxwell electrodynamics. All right. Okay, so next up, you might be interested in gauge theory. Pure SUN gauge theory has a ZN one-form symmetry, which is the so-called center symmetry of gauge theory. You've probably heard of this. The modern way to think about this is that this center symmetry is a ZN one-form symmetry, and the charged line operator is just the fundamental Wilson line in the gauge theory, all right? And this is, again, a very well-studied thing, but it was organized in this context in this nice paper I mentioned by Gaudo, Kapustin, Seiberg, and Willett. And finally, if you don't like gauge theories, but you like statistical mechanics, the normal 3D Ising model, you can think of it as having a Z2 one-form symmetry associated with the integrity of domain walls. So what does that mean? The 3D Ising model has a bunch of spins that can be either up, down, but you can think about domain walls that separate up from down spins. Those domain walls never end. And that's a dynamical fact that has a symmetry associated with it. This statement actually makes the most sense if you formulate this as a Z2 gauge theory, but let me not get into that. But the charged line operator is something called the 3D Ising defect, which people do study. Okay. So the point of this slide is just to tell you that many theories that you know and love quite possibly have these symmetries already. if there's ever an extended object in your theory that you're thinking about, it probably has this higher form symmetry. Okay. Okay. Are there any questions about this before I move on? Okay. Very good. So now there's a natural question. Very tempting now to try to define a new Landau paradigm. The new Landau paradigm is the following. Phases of matter are classified by their patterns of broken and unbroken symmetries, which includes these higher form symmetries now. Okay. And furthermore, critical points between phases should then be understandable by universal theories of the order parameter. So it turns out the first point works really well. Okay. It is a fact that many examples of topological order can be understood as theories that have spontaneously broken higher form symmetries. This just works. It's almost tautologically true. Okay. But now if you believe this, you might be tempted to think about point number two. Point number two suggests that just as we think about the condensation of particles for normal symmetries, we should think about the condensation of strings for these higher form symmetries. And that might describe interesting critical points into and out of topological phases. This is the point that I'm going to focus on for the remainder of this talk. Okay. So this finally concludes the sort of introductory part of this talk. And now I'm going to get into the actual meat of it. I'm going to tell you about this thing which we call mean string field theory. Okay. So here we go. What is mean string field theory? So to describe a transition where a higher form symmetry is spontaneously broken, we need a framework that is the analog of this Landau-Ginzburg type theory. Okay. I want to write down something that does for higher form symmetries what Landau-Ginzburg theory does for ordinary symmetries. Okay. And what's fun about this is that just like the Landau-Ginzburg theory describes the condensation of particles, this framework should allow us to describe the condensation of strings. Right. And this is a notoriously hard problem, of course. This might scare you a little bit because this sort of sounds now like string field theory. String field theory is a non-perturbative formulation that describes describes phenomena. It describes string theory not in a first quantized formalism, but a second quantized one. But we all know it's very, very hard. Okay. So we need non-perturbative formalism like that. We can't use a first quantized formalism for this. The point is, my goals are a little bit less high. I'm going to use these higher form symmetries. And unlike string field theory, traditional string field theory, I'm not going to demand that my theory be UV complete. Instead, I'm going to just try to study transitions, low energy physics. And it turns out, given this slightly relaxed set of expectations, it is possible to build something. So let's do it. Let us now try to fill in this box and build an object that is the higher form analog of this Landau-Ginzburg theory. So I'm going to construct everything by analogy with ordinary symmetries. So let me just remind you about some few basic facts. In this Landau-Ginzburg theory, as I argued earlier, my basic degree of freedom is a map from points to the complex numbers. It's just a field, phi of x. This phi of x transforms linearly under the symmetries. Phi of x goes to phi of x times e to the I alpha, where the global symmetry is such that d alpha equals to 0. Now, having said that, we can often couple this global U1 symmetry to an external gauge field A. This is a very useful thing to do for lots of reasons. If you do that, what you do is you demand the theory be invariant under a larger symmetry operation where phi goes to phi times e to the I alpha of x, where alpha now depends on space and time, and A is shifted by d alpha. You demand your theory is invariant under this larger symmetry. What we now need to do is build the analogs of these objects and this gauge covariant derivative for a higher form symmetry, for a one form symmetry rather. Okay, so first, what is the analog of phi of x? Now, a one form symmetry acts on line operators. Our basic degree of freedom then can no longer be a local operator phi of x. It must instead be something that's like a line operator. In other words, it must be a functional. It's a map from the space of closed curves to the complex numbers. Okay. So from now on, psi of c is going to take as an argument c, which is a closed connected curve, and it's going to spit out a number. This is my basic degree of freedom for the rest of this talk. Okay. And I'm going to call psi of c the string field. All right. This is the one form analog of phi of x. You can imagine just like phi of x made a particle, psi of c creates a string. Now, this one form symmetry acts linearly on psi of c. And the way to understand that is, of course, that psi of c is just rotated by a phase, where that phase is e to the I times the integral of gamma along this curve c, where d gamma equals to 0. Okay, this is the one form analog of this thing right here. However, it's often nice to be able to promote this to a more general symmetry principle. In other words, I'd like to be able to find a way to couple an external two-form source to this field in such a way that I can shift psi of c by psi of c times e to the I integral of gamma, and shift b by b goes to b plus d gamma. So I'd like to be able to do this in some way that makes sense. So how do I do this? How do I write down a term that lets me couple things in this manner? It turns out that I'm going to have to differentiate this string field, right? Because if I want to write down a theory, I need to have a kinetic term for my degree of freedom. And this kinetic term is going to come from something like this. So how do I differentiate a functional of curves? It turns out the required machinery was already constructed by people like Iqbal and Polyakov many years ago. It's something called the area derivative. So what is the area derivative? The area derivative tells you how to compare the field between two nearby curves. So what does it mean for one curve to be nearby another curve? The idea is, you imagine taking your string field defined on some curve C, and then you add a little loop here, delta sigma, okay, to this curve. Now your string field is going to shift when you do that, but if sigma is very small, it should shift just a little bit, it should shift linearly in some sense. The coefficient of that shift as a function of the area element, delta sigma mu nu, is the definition of the area derivative. Okay. And this is basically the same as the normal derivative, right? The normal derivative, you shift your field a little bit, the field changes a little bit, you call that coefficient of that shift the normal derivative. This is the string, this is the sort of loop space analog of a normal derivative. Now, this sounds formal. There's a definition given in these papers. You can use this definition in principle to actually compute the derivative of any functional. Let me give you some examples. So one functional which comes up often is the following. Imagine you have an extra one-form gauge field A, and you integrate that one-form gauge field along a curve C. That's a functional of the curve C, right? The area derivative of that functional is the field strength F associated to that gauge field. That should make sense, right? If you look at what's happening here, if you have integral of A along this curve, if you add a little element here, and you have to integrate A along this curve as well, then you use Stokes' theorem to make that integral of A into integral of F over the interior, and you have this formula right here, provided this thing is F. Okay, so this should sound reasonable. It's a slightly less obvious one. Let's consider the following functional, which is the minimal area functional. In other words, given a curve C, find the minimal area that fills this in, and then ask what is the area derivative of the minimal area functional. The answer turns out to be the outer product of the tangent vector to the curve and the normal vector to the curve along the minimal area evaluated at this point where you're taking the derivative. Okay, this is a very nice and very geometric thing. It should again make some sense, right? If you add a little bit of an area element here, you'll have to increase the area. The amount that you increase it is going to depend on what's there already. You can prove this through starting the tedious computation, but it can be done. Okay. Okay. Any questions about the area derivative and the string field before I move on? Okay. I'm not seeing anything. Good. So now, moving on then. So now I can construct an area derivative that lets me couple an external gauge field source to the string field. And that object is the following. What I do is I take the normal area derivative and then I multiply it by I times the two-form field B. Okay. If you look at what happens, if you now do this transformation, psi to psi times e to the I integral of gamma, the area derivative picks up a factor of d gamma from the previous slide. So you have to shift b by b goes to b plus d gamma. And then this whole thing is invariant. So this is the gauge covariant version of this higher form symmetry. no, it's kind of cute because this area derivative, which was understood quite a long time before this higher form global symmetry stuff, is exactly the right thing to make this possible. Okay. So now that we know it's possible, I'm going to set B to 0, but we can always put it back if we want to, okay, through this sort of minimal coupling, now that we know we can do it. Okay, so we have almost all the ingredients that we need. So finally, I'm going to take the integral over points that appears in my normal action and replace it with an integral over curves. Okay, so an integral dc. So this integral over curves is the regular functional integral over loops. This is this is something that we know how to do. This is a little annoying. Okay. So given all these ingredients, let me now state action, post-action for mean string field theory. So the action is really just an analog of the same ideas for normal Landau-Ginzburg theory. What you do is you start to write down terms that are invariant under the symmetries, and you do it the same way. You write down a kinetic term. This kinetic term involves this area derivative. I have to integrate it over the whole curve, okay? But this area derivative term here is the analog of the normal kinetic term. I can write down a term like m squared psi dagger psi, because that is clearly invariant under the U1 phase rotation that I mentioned earlier. I can write down a term like lambda psi to the fourth, because that's clearly invariant, and so on and so forth. I can't obviously write down a term like psi cubed, because that would not be invariant. All right. So the idea is the same, just like normal Landau-Ginzburg theory. You want to write down the most general dynamics for the string field that respects these symmetries. One difference, of course, is that the integral now has to be taken not over all points, but rather over all curves. And I just have to do that because my field depends on curves. All right. So now here's a question. This is a difficult, but it's a well-posed problem. I've just written down for you a theory. What does this theory describe? Okay. And for the rest of the talk, I will just tell you what this theory describes. And before doing that, though, I'm going to just say a few caveats. If you are doing real Landau-Ginzburg theory, write down the most general action that you can. This thing I wrote down actually isn't the most general. In a few slides, I'll show you some examples of, I've left out a few things. That's because they're hard, okay? But I will show you what I've left out, and I'll argue about how I think it changes the problem. But this is not the most general thing. And finally, this is a string field theory. And we thought we were making this up, but it turns out we learned much later that actually similar theories had been written down quite a long time ago, because Suzhong Rei wrote down something very similar in 1989. But the application for that was to fundamental string theory, the normal string theory that describes quantum gravity. We're not trying to describe that here. We're trying to describe the low energy dynamics of phase transitions involving one-form symmetries. So like gauge theories, lattice gauge theories, things like that. That's what we're trying to do here. In particular, this theory is going to be completely wildly non-UV complete. All right, and we'll see that as we go on. Okay, so this is the theory that I will now describe for the rest of this talk. Pause again. Any questions? Okay. Okay, good. So now, let me now describe the different phases of mean string field theory. So of course, this, by the way, is mean string field theory. It's called string field theory because it's non-perturbative in the creation of strings, and it's mean string field theory because it's really an effective theory. Okay. Okay. Let me now tell you about the phases of mean string field theory. So first of all, we can have an unbroken phase. In the unbroken phase, m squared is positive, very positive. So my potential has a single unique minimum. Okay, it looks like this. Now, okay, so in that case, what you're tempted to do is ignore the interaction terms for a second. Just think about the quadratic part. And let's just ask, there are some classical equations that come out from this. They look like this, okay? This is a well-posed equation, but it's complicated. It's a linear equation in functional space because psi is a functional. It's kind of hard to solve this equation, even though it's linear. I think it should be possible to solve this equation. It's hard to solve this linear equation in full generality. There are some conceptual issues associated with what is the meaning of loop space, and there are some calculational issues associated with the fact that I don't really know how to capture all the data. There's a lot of data here because psi can depend on this functional in a very arbitrary way. So instead of trying to solve this equation in full generality, let me just try to solve it in the limit where this curve C is very large. Okay. So in particular, I'm going to try the following WKB-inspired ansatz. I'm going to assume that the full dependence on this curve C enters only the following way. It enters only as a function of the minimal area A that fills in this curve. Okay. So my string field depends only on that minimal area. And I'm writing it like x minus s, excuse me, this s is not the same as that s. I'm just writing it as x minus s as a function of A, because this is inspired by WKB. When you do WKB type stuff, this is a useful thing to do. So now if you take this ansatz and you plug this into this equation, what you find is a very simple equation for this function of one variable s. The point is the area derivative works really nicely with this minimal area functional. These two things fit really well together, and they end up giving you an equation which is just s prime squared equals to m squared, plus terms which are subleading in A. Okay, and this you can verify from the definitions I've given you. I won't do this in real time. And therefore, the solution to this is just that S is linear in M. And so the string field then in the unbroken phase behaves like an area law. Okay. So this is really a genuine area law where this area is a minimal area. And this is, of course, exactly the expected behavior in the unbroken phase. So now it's fun to take a step back and think, well, what's really happening here? This area law is normally understood as an order parameter for confinement. We are seeing the same thing here, but of course there's no gauge fields or anything in this problem, okay? Well, what is present is the same symmetry that was present in the gauge field problem, is present here. And we can see that that symmetry alone, the unbroken center symmetry, is sufficient for you to derive this area law. So this is sort of a nice thing. And there's some interesting questions here about how to relate this to other formulations of non-abelian gauge theory, in particular the loop formulation of QCD by Migdal and Makenko is attacking this problem from a very different point of view, but has a very similar result. Okay. Are there any questions before I move on? Okay.
So I might have one.
Yes, please.
So, but what have you shown exactly? Because I mean, you assume a very particular answer, right, for the function.
Yeah, that's right. That's right. It's the truth is, you're absolutely right. I've shown there exists a solution that behaves like this. I have not shown that it's the only solution. I've just shown this is a solution, I think. That's what I've shown.
And I might have another stupid question.
Yeah.
So what makes you be so what now restricts you to take just like a two derivative theory in this
Yeah. No, very good. You should really add every derivative. However, they will be less relevant than this.
Yeah, that's what I was saying.
Same reason. So you can argue that those terms are less relevant and so will not affect this result. That you can argue. For the same reason as a normal Landau-Ginzburg theory, where of course you do actually have higher derivative terms. They just don't affect the leading long distance behavior.
Okay.
Yeah.
Thanks.
Very welcome. Thank you. Any other questions?
Sorry, I have one. So would it help if you would try to write down some of the known examples? For example, take domain walls in 3D Ising. So
yeah,
look like in this formalism.
Yeah, you could. I mean, you could do that. The 3D Ising example has a Z2 one-form symmetry. Mm-hmm. So it's not exactly this one, but it's very similar. You just have to, instead of having size real.
Sure.
Yeah. And then you have like psi to the fourth. You don't have psi to the cubed. And you can, on same grounds, argue that in the unbroken phase, this will happen. That's right.
Same form. Okay.
Yeah, the same form. Because notice this result actually didn't care about the interaction terms. It only cared about the quadratic part. Because I'm neglecting them. Yeah.
I see.
But you get the same answer. Yeah.
Okay, yeah. I see. Thanks.
Good question. Any others? Okay, great. Thank you. So now moving on, this is the unbroken phase. But then let me ask you about the broken phase. All right. So in the broken phase, what you do is you look at a phase where the m squared can be negative. All right. In that case, the potential looks like this. And now the action is minimized at a non-zero value of psi, at the minimum of this potential at this value v. So on general grounds, you now expect there to be a gapless Goldstone mode. Okay. As I mentioned, we've proven this. You can prove this on general grounds, but it'd be good to see this happen explicitly. So how do we see this? One way to understand the Goldstone mode is that you do a global symmetry transformation, but then you do that symmetry transformation in a way which depends on space. In other words, you allow the coefficient of the symmetry to vary in space-time. In this case, because it's a one-form symmetry transformation, you have to write down a vector field, which I'm going to call little a, and integrate that vector field along the curve C. Okay. So the question is, if I take now this form here, where I'm modulating this thing by a space-time symmetry transformation, and I plug this back into my ansatz, can I derive an effective action for this field A? And if I can, what does that effective action look like? Okay, so let's do this. So the point is, you take this string field. Yeah, sorry.
Nabil, may I ask one question?
Sure.
Is this where does the U1 symmetry come from?
So I'm studying a theory that has a U1 one-form symmetry. So it's there from the beginning. So I'm assuming I have this U1 one-form symmetry.
But you're not connecting it to an open or closed string microscopic description.
No.
It's there.
Yeah, exactly. This is just like in as I was saying, there's a higher form global symmetry. So I'm assuming I have a higher form global symmetry from the outset.
Yeah.
So a concrete example to keep in mind is just normal Maxwell E and M. That is a higher form global symmetry.
Yeah. Thank you.
Yeah, very well. Good. Other questions? Okay, good. So I have this this string field ansatz. So now I'm going to plug this into this action. Okay. So all the fun comes from the kinetic term. Let me focus on the kinetic term. So what happens if I do this? Well, you can see that these area laws are going to bring down factors of f. These area derivatives, sorry, are going to bring down factors of f because the area derivative always takes the derivative of these gauge fields. So you end up getting an f squared from this term and an f from this term. So I end up getting an f squared is a factor of v squared out front from this v over here. And what you see is I have some sort of complicated integral over curves of f mu nu, weighted in some fashion. Okay. Okay. But now we can do this integral over curves. This is a normal problem in sort of world-line quantum field theory. Technology is to do that. So if I do that integral over curves using, for example, the techniques that Matt Strassler and company developed, what you end up finding at the end of the day is that the effective action for this degree of freedom A is just f squared times a number. Okay. So you end up getting, as claimed, a gapless Goldstone mode. Okay. Well, let's take a step back for a second and think about this. If you'd like, this is a way of understanding where the normal massless photon in our universe comes from. I don't know if you've ever lain awake, wondering why is the photon massless? You see, when I teach quantum field theory, I tell students the photon is massless because of gauge invariance. But the truth is, that's actually kind of a lie, right? Because, for example, a superconductor is completely gauge invariant, yet the photon is not massless in that phase. So, what do I mean? Then you start saying words like, well, the photon is massless if you have gauge invariance and the gauge symmetry is not spontaneously broken, but there's no such thing as spontaneously breaking a gauge symmetry. That's not a gauge invariant concept. And you get into weird philosophical dilemmas. The point is, I claim the right way to think about this is the following. You have a genuine one-form global symmetry associated with the conservation of magnetic flux. That one-form global symmetry is genuinely spontaneously broken, as diagnosed by these line operators. And the 4D photon that we know and love is the genuine Goldstone mode of that symmetry breaking. That's why it's actually massless. And this point of view, I want to stress, is not something novel to us. This is present in the very first paper by Gauda, Kapustin, Seiberg, and Willett. But it's nice to see that this whole thing is consistent, and you can derive that from a sort of effective Landau-Ginzburg type approach. Okay. Okay. So, any questions about this? Did I heard something? No. Okay. Good. So next up, I want to talk about something else, though. You see, you might now be a bit concerned because my string functional has many degrees of freedom. I just told you about one of them, but you could imagine modulating that phase in many different ways. And because the action doesn't care about the phase, you might think there are many gapless modes, and that would be weird because real-life systems shouldn't have many gapless modes. So for example, you might imagine modulating the phase in the following way. You might imagine adding not just this vector phase modulation, but a scalar phase modulation. Okay, so I add an extra field T of X, and I just modulate each of that T of X. You might think this will give you an extra gapless mode for T. That would be worrying. But it turns out if you repeat the same calculation, you actually do find a mass term for this T of X field. In fact, it's gapped out at a very high scale. It's gapped out at the UV cutoff scale. All right. That happens calculation because this area derivative acts on the measure ds in this integral for this T of X in a particular fashion. Physically, it happens because there's no symmetry protecting it. Okay. This A shifts under the one-form symmetry. So it's really protected by symmetry. This T of X does not. And that's why it receives a mass. Okay. In fact, I see no evidence for any other gapless modes. This just emphasizes, by the way, that this is not real string theory. There's no secret gravity lurking in this problem. Okay. It's really something different. It's an effective description of higher form symmetries. It's not real fundamental string theory. Okay. And finally, if you care not about the U1 symmetry, but a discrete symmetry, it turns out you can reproduce the affected topological quantum field theory that you expect in the broken phase from these considerations. It's a little bit silly and kind of tautological, but you can get it. Okay. Okay. All right. So I'm almost done with the results. But let me now say one more thing. You might now be curious about the transition, right? Because I now have a mean field theory. You might be curious, does this mean field theory correctly describe transitions where the symmetry is spontaneously broken? And in fact, this statement, this equation for the area law can be understood as telling you there's a mean field transition at m equals 0, right? That's where you cross over from the positive, the unbroken phase, the spontaneously broken phase. And there's a mean field transition at m equals 0. When I say it's mean field, I mean that the string tension will diverge like a square root, not diverge, sorry, will vanish like a square root at that critical point. Okay. This kind of transition is, of course, normal for mean field theories. In normal mean field theory, the correlation length diverges like a square root at the critical point. This is the same thing, but for string tension. So now there's a really strong temptation to compare this to experimental data and ask, does this do a good job? Does this correctly describe it? So what can I compare it to? So one thing you could do is look at the 3D Ising model. The 3D Ising model has such a transition, and the scaling of the string exponent has been calculated numerically. They get an exponent here, and that exponent is 1.26, which is very different from 0.5. So I have done a very bad job at calculating, at deriving the string model. Okay, that's fine, but what does that mean, really? What that means is, this is the description if you ignore all these interaction terms. In other words, if you have a sort of free string field theory, this tells you that the 3D Ising model is not well described by a free string theory. We might have expected that, to be honest. In fact, people have tried to solve the 3D Ising model using string theory, including me, and we find that it doesn't really work because the string theory is always strongly coupled. This is completely consistent with that fact. Okay, now let's think about it from the point of view of this mean field theory. If you were trying to use mean field theory to describe a transition, what you should ask is, the interactions that you have neglected, are they relevant at the transition or not? If they're relevant, then they will invalidate your weakly coupled description. It's actually rather complicated to do this dimensional analysis in our case, but if you try to do a very naive estimate of the dimensions, what you find is this side to the fourth coupling is relevant in D equals to 8 and below. In other words, the upper critical dimension of mean string field theory is 8, at least. It might be even higher, but it's at least 8. Okay. This is kind of cute because it turns out that Parisi years ago had actually speculated on this same number 8 from a very different point of view. I can't quite make the connection precise, but I find it interesting that he had the same number. But what that means is that these transitions will be strongly interacting in all dimensions less than 8. And therefore, I do not expect my mean string field theory to be quantitatively correct in any dimension less than 8. 3 is much less than 8. Okay. But by showing this slide, what I would like to ask people is, this is describing a continuous confinement-deconfinement transition. If you happen to know of any in higher dimensions, the higher the dimension, the better, please tell me, because I would love to see if there are higher dimensional examples in obscure finely tuned field theories that I can test this framework on. Okay. All right. Good. So I'm almost done. I want to, in interest of disclosure, I want to tell you things that I neglected, okay? And if you're doing a Landau-Ginzburg description, you want to write down the most general action that you can. I actually didn't write that down. Let me tell you what I neglected. There are terms that are intrinsically stringy that have no zero form analog, and the terms look like this, okay? So what's happening here? This is an integral over 3 parameters and not 1, okay? But it's a delta function in loop space, all right? And what does that mean? This tells you that the integral is non-zero unless C2 plus C3 equal to C1, which means that they fit together in this way, okay? And this term is actually invariant under everything that I wanted, okay? What it represents physically is that 2 strings are merging together to make a bigger string, all right? And this is physically quite reasonable, okay? It makes complete sense, and I think it's important, and we should include it. It's really kind of hard to deal with though, because first of all, I am not sure whether this really exists. There's some confusing discussion about what is locality in loop space? Is this local or not? I don't really know. There's 3 integrals, but it's a delta function, but it's a weird delta function. You can really wonder whether this term should be allowed or not by the principles that I've put down. So this is some confusion that I have, but it's likely important, but we don't know how to treat it systematically yet. We're working on it. It is possible to treat it systematically, I think, but we've not done it yet. I think it's important at the transition. In particular, it is likely to alter the transition from what I told you, and it also may affect the upper critical dimension. Okay, but I don't have enough control over it to tell you whether it makes it higher or what. And finally, the couplings in the action, I assume they were constant. And in normal field theory, they are constant by translational invariance. But it turns out that here, they can actually depend on the length of the curve, okay? Because the length of the curve is a local functional of the curve, which is invariant under every symmetry. And we could not find a symmetry principle that would rule out things like this. Like, for example, the mass is not just a constant. It's like, as a term like 1 over L to the L square, blah, 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 and so on. These look like they're irrelevant, these couplings, but they could be important at the phase transition, especially if you tune some of these couplings to 0, especially if you want to compare with the lattice. And so we don't know how to control these terms yet. And I think this is something that we need to build some control over. And really, both of these issues are telling us that we don't really know how to think about the relevance or irrelevance of these terms in a systematic way. We can look at their dimension, but I don't think that's really sufficient in loop space. So we need a framework for doing RG in loop space to really make sense of these terms. And this is interesting and I think quite possible. We're working on this actively now. One can do quite concrete calculations, but we've not been able to make too much sense of it yet. Okay, I'm almost out of time, so let me just conclude with one brief philosophy slide, and then I'll summarize. You see, here's a little bit of philosophy. There's a grand tradition from the 70s to reformulate Yang-Mills theory in terms of gauge invariant loop equations. People like Migdal, Makenko, Polyakov, and so on have tried to reformulate things in terms of loop equations. Okay, and that's a great thing to do, and it's a very beautiful subject. But now, from a modern point of view, I might ask you the following question. What is Yang-Mills theory exactly? Okay, Yang-Mills theory is a theory with gauge symmetry, but gauge symmetry isn't a symmetry at all. It's just a redundancy of our description. Okay. So someone gives you, for example, a chunk of metal or a piece of ADS space and says, is this a gauge theory? How do you answer that question? It's really not clear. And it's not clear to me this question has an answer. Okay. Here's a candidate answer. Pure Yang-Mills theory is a theory that has a Zn1 from global symmetry. Okay. It's a fact that it has that global symmetry. That global symmetry is an unambiguous thing. You can test your piece of metal and see if it has this global symmetry or not. And so what I'm trying to do in this framework is to try to build the dynamics around that global symmetry and not around any sort of auxiliary gauge degrees of freedom. From that point of view, it's kind of nice that the simplest way to build dynamics around that organizing principle, which I think is what we've done, does actually give you an area law in the unbroken phase. It gives you this hallmark of confinement. And it's fun to try to keep pushing on this and see if you can really get all the structures of gauge theory from this very different manifestly gauge invariant formalism. Okay, so this is the hope. Let's say a few future directions. Really, you have to take this theory, or what we're going to do is we'd like to take this theory and just do everything we do from normal field theory with the theory. So for example, you should construct the propagator. Okay, this tells you the chance for a string to go from here to here. This is a very well-posed thing. There's a differential operator. You want to invert it. It's a complicated differential operator, but it's a linear problem, so we should be able to do this. And you can then build perturbation theory from that propagator. It's very interesting to ask what's happening. I'd like to connect this to data. In other words, I'm not really sure I understand the order of the transition in our theory. If you look on the lattice, most confinement, deconfinement transitions above d equals 3 are first order. It'd be good to confront this with our theory and see if this makes sense or not. To me, this is a sort of new motivation to look for continuous transitions on the lattice. In particular, you could do numerics on the lattice and look for continuous transitions and compare them to our theory, something we'd like to do. Another thing is the upper critical dimension, d, which I think is 8, but might be higher. Normally, if you have an upper critical dimension, you can do a d minus epsilon expansion above the upper critical dimension. For normal field theory, this is a 4 minus epsilon expansion. For us, it would be an 8 minus epsilon expansion or worse. But what this suggests is you could try to balance this scaling and try to build a new critical point using this theory. Okay. This new critical point would not have a conventional Lagrangian description, probably. It would be built around these stringy concepts. But it's very exciting to wonder, can I use this to describe these exotic theories and string theory and so on that are known to not have known Lagrangian descriptions? Finally, there are some things that might leave you uncomfortable about this theory. Honestly, it has way too many degrees of freedom to describe a local theory. On the other hand, they're all gaps. Does it matter? You could worry about this. And the issues of universality that I mentioned have to be addressed. Okay. But the longer term questions are really, if we use these symmetries, can we build a new Landau paradigm? What does it include? Does it include all phases of matter? And can string theory help us build this new Landau paradigm? Can it help us understand statistical physics? Or vice versa, can statistical physics help us understand non-perturbative ways to formulate string theory? Okay, thank you for your attention. I've already gone 3 minutes over, so I'll stop right now. Thank you again.
Thanks a lot, Nabil. Very nice. I see a raised hand by Giorgio. I don't know.
Hi. Thank you for a very nice talk. Very interesting. I have a sort of simple physical, and maybe my intuition is totally physically off, but as we know from, here's a physical system for you. What happens if you put a bunch of cables in boxes and take them around and shake them and then open the box? I'm sure many of you. And the protein folding problem, and I mean, in some sense, the string landscape is sort of the same thing, that free energies in theories where strings are degrees of freedom have an enormous amount of local minima to such an extent that there is no fluctuation. Any fluctuation dissipation is disturbed by the fact that the rate of tunneling between minima is comparable to, is such that it doesn't make sense to speak about minima, if you see what I mean.
Yeah, right.
Does this appear here or not?
No, that does not seem to appear here. And I think what we should do is think about why. What is the extra physics in the examples you gave that is not present here?
Sure.
And I think it has to do with the fact that those examples, there's structure in the fact that, the cables in my box, they can't go through each other, right? That's why this problem is so hard, because there's lots of data encoded in how many times they wrap around each other, because they can't go through each other, right? Sure. And I don't know anything about protein folding. I'm gonna not say anything about it, but I imagine it's hard because details are important. And here there's no such structure. The strings can pass through each other freely, I think that's why there's no, you don't have this weird rich landscape of minima here. You really have either a unique minima or a set of minima that are connected by symmetries like this symmetry broken phase.
Just to sort of say QCD, the confinement picture of QCD in terms of Polyakov, in terms of Wilson loops and Polyakov loops, might actually have an analogy with cables, in the sense that there have been believable attempts to link confinement to turbulence, to the fact that these Polyakov structures are all unstable unless Z3 symmetry is exact and stuff like that. So
right. No, absolutely. I think turbulence is very interesting. So I was heavily influenced actually by Migdal's work on the same. He's using the same technology that he used for non-abelian gauge theory for turbulence. And I think it's an interesting analogy. I think it's not super clear to me. Like, you know, the turbulent state, it's not clear to me that has many local minima. In fact, it appears featureless, right? The turbulent state, it has power law correlations, and there's one unique turbulent state. So I think it's super fun to think about, but I'm not sure that anything in there is inconsistent with the idea that there's a simple, you know, a simple vacuum structure if the things can move through each other. I think that.
So you don't have many local minima in any of your phases, right?
No. That's right.
It's a little bit hidden behind the fact that it's a functional of curves. You see what I mean?
Yeah. That's right. I mean, to be completely honest, I have not been able to solve this theory completely. So it's quite possible that if you like this, which are quite complicated, you get new minima that I have not thought about. So that's a possibility. Having said that, I would be surprised, to be completely honest.
A term like this, I could think of could lead to lots of things that just add up to zero.
That's right. Exactly. It's possible, but I would be surprised if there's many local minima. You know, my current understanding is that these things, they change the minima that we found, but I don't think they result in entirely new families of local minima. The sort of glassy dynamics you'd need for that. I don't see any evidence for that, but if I'm wrong, that would be very interesting. So, you know, yeah, excellent question.
Thanks.
Hi, Nabil.
Hi, Richard.
Hey, thanks very much. That was really interesting talk. I have a question. I guess it's kind of related to what you wrote on your philosophical questions slide. Is there any prospect of understanding gravity through some kind of higher form global symmetry?
Yeah. So to be honest, I really think there should be, because the graviton is massless, and I have to confess I don't really understand why at some deep level. Again, the same set of wrong words that
right, yeah, exactly.
Yeah. Applies to that as well. So I really think there should be. It's not super simple to. I can tell you what I've tried to do. You really expect there to be some sort of spontaneously broken higher form symmetry associated with some aspect of gravity. I think there's also indices that make it hard, and also there's this lore that says that there are no global symmetries in gravity, right? So there's some tension between this set of ideas. Having said that, I kind of feel like there should be some way to think about an approximate higher form global symmetry that's spontaneously broken in some way that protects the graviton. It'd be really fun to understand that. I've not tried. I think I've played with some of the equations, but there's so many indices that I get tired quickly. But I think it's worth exploring in detail. I feel like there's really analogies between E&M and gravity that one could push on much harder than I think we have at the moment. But I think it would be fun to do. I think the short answer is I believe this is correct, but I have absolutely zero evidence for it calculationally. Yeah.
Okay. Great. Yeah. No, that's a interesting answer. Thanks.
Okay.
More questions? Okay. So if there's no more questions as usual, okay. I see Martin has raised his hand. Martin, you're muted.
Okay. Yeah, my computer is dying. I don't know why. So you make this argument that you look at this kind of Goldstone boson now for this higher form symmetry. But like if you go back to the conventional zero form symmetries, then of course we should first ask the question, why do we have this manifold of vacua? And then of course we argue classical decomposition principle and so on. So do you think a similar argument also applies here in the case of strings?
I think that cluster decomposition is very strange. I wouldn't know how to think about it, to be honest, because I have very little understanding about the sort of locality in loop space is really weird. Like, I don't think I have a good understanding of it. So I'd be nervous about saying things about cluster decomposition, I think. I'm not sure I understood the beginning point, though. You're asking, I think the question is, there's this manifold of vacua because there's a U1 global symmetry. And I guess you're actually saying, how do we know that the quantum corrections don't lift the degeneracy? Is that correct? Is that right? Okay, very good. So that's sort of like asking about the lower critical dimension, right, of the symmetry breaking. In other words, if your dimension is less than 2, less than or equal to 2, the correlators of the order parameter decay only algebraically, and not, this is what you're talking about. Is that correct, Martin? No.
Yes, partly, yes.
Yeah, so that you can actually ask, actually. You don't need to use our formalism. You can just ask it in general, higher form symmetries. And it seems that the number for the lower critical dimension is shifted. I believe for a one form symmetry, it shifted from 2, I think it shifted to 3. I can't quite recall right now, but it's in this nice paper by Ethan Lake. They work out lower critical dimension. And so what that means is that basically it seems that the same effect happens, but the kinematics is just a bit different. You know, like cluster decomposition and so on, locality, the sort of quantum effects are sufficient to lift the degeneracy, I think, in dimensions less than or equal to 3 rather than less than or equal to 2. But except for that, it's the same idea. Did that answer your question? No.
Yeah, I think so, yeah.
Good.
Okay, we've had some questions. Okay, if there's no more questions, I will like officially close the talk and then ask again if there are more shy or unofficial questions. So thanks a lot, Nabil. Very nice. As you saw, there was a lot of interest in your talks. Very nice.
Thank you.
And see you all probably in 2 or 3 weeks. Just look at the web because we are like setting the new talks. Okay, let me stop the recording.